Hello students, today let us find the electric field due to an electric dipole at an equatorial point. Last class we have discussed about an electric dipole. We have found the electric field due to an electric dipole at an axial point. Today we will find electric field due to an electric dipole at an equatorial point. What is the meaning of equatorial point? Equatorial point means it is a point on the equatorial line. What is an equatorial line? It is the imaginary line which is passing through the center of the dipole and perpendicular to the axial line. Now I have taken one electric dipole having charges minus q and plus q. They are separated by a distance 2a, and this is the dipole moment. This is the direction of dipole moment which is directed from minus q to plus q. We want to find the electric field at a point P which is at a distance r from the center of the dipole. Now OP is equal to R. OP is equal to R. And AB is equal to 2A, distance between the two charges. So AO is equal to A, OB also equal to A. What about the distance BP and AP? AP and also equal to BP, both are equal to R square plus A square square root. So as usual, we will find the electric field due to the minus charge, minus q, then electric field due to plus q, then we will take the vector sum to get the field, the resultant field at point P, and this is due to principle of superposition. To find out the field due to minus q and plus q, we are applying the electric field due to a point charge. You know electric field, formula for electric field due to point charge, that is E is equal to 1 by 4 pi epsilon naught q by r square. Now let us write the electric field due to minus q. So electric field due to minus q, that is equal to 1 by 4 pi epsilon naught q by r square. What is the direction? This is minus q. So you know for negative charge, field is directed towards the charge from the point. So q by this distance is r square plus a square square root. So it is r square plus a square square root whole square. What is the direction? Along PA. So this is the direction of electric field from P to A. It is directed from P to A. This is E minus Q. Similarly, what is the electric field due to plus Q? So E plus Q is equal to 1 by 4 pi epsilon naught Q by again r square plus a square square root whole square along. So it is directed away. So this is the direction of E plus Q, which is directed away from the charge. Right? So along BP. Now we have got two fields. One is E plus Q, one is E minus Q, and we have to get the resultant of these two fields, E plus Q and E minus Q. Let us find the resultant field. How to get this one? Two different methods are there. We can apply the parallelogram law of vector addition, or we can resolve into components, resolution of vectors. That also can be applied. Now let us divide. See now, the magnitude of, if you see E plus Q and the magnitude of E minus Q, both are same. Let it be E, say E plus Q and E minus Q, magnitude as both are same, I can take it as E. So now, see, we can resolve these two vectors E plus Q and E minus Q into two components, two rectangular components. Now this vector can be resolved in two components. One component parallel to the dipole axis, another component perpendicular to the dipole axis. Now say this angle theta means obviously this angle will be theta. Now which component E cos theta? So this component will be E cos theta and this component will be E sin theta. Similarly, the components of E minus Q. So E minus Q is like this. And I have taken equal to E. So this will have also two components. This angle. So this angle theta means this angle also theta. So it will have two components. What are the two components? Here one component, here one component. This component is here downward, this component is towards left. So again E cos theta and this component will be E sin theta. Now see children, the components, when we are adding the components parallel to the axis, they add up because both are E cos theta acting along the same direction. And when we are adding this E sin theta and E sin theta, they are in opposite directions. So they get cancelled out. So total field is equal to E equatorial will be equal to E equatorial will be equal to 2E cos theta because they are added up. As now you can write here, you have to write resolving the two fields into components, rectangular components. The components parallel to the axis add up, whereas the component perpendicular to axis gets cancelled out. So now total field E equatorial equal to 2E cos theta. I will put the value of E and value of cos theta to get the resultant field. And one more thing you see, the direction of the resultant field is opposite to the direction of dipole moment. So now let me write the value of the resultant field. So value of resultant field is now E equatorial 2 into E value is 1 by 4 pi epsilon naught Q by R square plus S square. And what about cos theta? So any triangle can be taken. You can take OPP or OAP to get the value of cos theta. And cos theta is here. Here if you take this triangle, this value is A and this is given. So A divided by R square plus S square root over. That means 1 by 4 pi epsilon naught 2QA divided by R square plus S square to the power 3 by 2. And you see children, 2QA is nothing but P, dipole moment. So that is equal to 1 by 4 pi epsilon naught P divided by R square plus S square to the power 3 by 2. So this is the magnitude of the electric field at an equatorial point. What about the direction? The direction is opposite to the dipole moment. So now to write this field in vector form, we have to multiply unit vector in the direction of the resultant field. And unit vector is opposite to the direction of dipole moment. Last class we have taken, it is P cap. So I can write the resultant field at an equatorial point as, so E equatorial will be equal to, that is equal to 1 by 4 pi epsilon naught. Let us write this full form. E equatorial equal to E equatorial in the vector form, that is 1 by 4 pi epsilon naught P by R square plus A square to the power 3 by 2 minus P cap. Why minus P cap children? Because it is opposite to the direction of dipole moment. That's why minus P cap. Now as usual we will take a special case. The special case for a far equatorial point or for a short dipole, when the field point is at a large distance from the dipole, it is called a short dipole. For a short dipole, or when R is very greater than A, so A can be neglected with respect to R. So this implies E equatorial will be equal to 1 by 4 pi epsilon naught P by R cube minus P cap. So this is for, it is a special case. It is a special case for a short dipole. And for short dipole, you have seen that E axial, that is equal to, you know, the 1 by 4 pi epsilon naught 2P by R cube, that is P cap. You see now, for a short dipole, the electric field at an axial point and electric field at an equatorial point, they are in opposite direction, and magnitude is double the magnitude of the E axial is double the magnitude of E equatorial. So I can write the conclusion: for a short dipole, E axial, the magnitude of E axial is equal to twice the magnitude of E equatorial. Sometimes children question is coming, what is the angle between the axial field and the equatorial field? What is the angle between axial field and the equatorial field? So in that case what we can write, the angle is 180 degree. They are in opposite direction. For axial point, it is in this case like that. In the axial point, field is acting along the direction of dipole moment. For equatorial point, it is acting opposite to the direction of dipole moment. So the angle between the axial field and equatorial field is 180 degree. And for a short dipole, the magnitude of the electric field at an axial point is double the magnitude of the equatorial, the field due to an equatorial point. So this is all about the electric field due to an electric dipole at an equatorial point. Thank you.